Okay, I am recording. That's all my PPI stuff. Ignore that. And that is not even important. All right. I'll just wait a few more minutes. Does anyone have any questions about what we went over last class at all? Everyone understand it pretty well?
For the review, can we go over question 5 on Tuesday?
For the homework?
Yeah.
Yes. We can.
Okay, thank you.
Hey, Thomas. Oh, yes, I forgot.
Stick on my desk.
What?
Stick on my desk.
Oh, that's usually back there. For like, I think like flag or whatever, would get propped up somewhere, but I don't know what else to do. I don't know, I should save it to throw at one of the other professors.
Oh, you should.
Go. Did I hand you a card?
Yeah, you give me one.
I didn't give you one, no. Alright. Irving, I gave you a card, right?
Yeah.
Okay. Man, you guys really did not like homework 4. Everyone got problem 5 on homework 4. Extremely wrong, by the way.
Is the homework curved?
I was lenient on the grading. I even thought about like grading, excluding home problem 5 from grading entirely, but then I would have had to go much more harshly on everything else, which some students would have benefited and other students would have been killed. So because of that, I was just like, I'm just gonna grade it as is, especially since some students actually kind of got number 5 right, even though their procedure was right, but they just messed up certain things. What tripped up everyone on homework on problem 5? That's what I want to know. Yeah. Like, I know I made a grammatical error. It wasn't a statically indeterminate bar, and I was hoping that wasn't the reason why y'all got messed up. But like, I mean, I figured like even if it was statically indeterminate, you still would have had to solve that problem specifically anyways.
Did you collect these yet?
Which one is this?
5 and 4.
Yep, I will take these. These are both going. I will take that. And then I will place homework 5 there. Wait, who said they're confused about transformation of stresses?
No, I said I'm so excited to apply transformation interest.
Did you watch last class?
did.
You did?
Yes.
Transformation of stresses is fun. And today we're learning a more fun way of analyzing stresses using circles. Some of you will love it. Some of you will absolutely hate it.
Circle method.
Yes.
I don't know what that is.
Yeah, I'll show you guys. All right. So today we will be going over a concept. I was calling it circle method last class, but the actual method is called Moore's circle. And this relates to the transformation of stresses also. Now, do we remember what the three equations were for the transformation of stresses? So my first question is, what was sigma xt? Who can tell me that?
Sigma x plus sigma y over, or divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta.
Good. Now, these equations don't just come out of nowhere. There's a lot of like force equilibrium and analyzing the internal equilibrium through different rotations of these to really come up with these generalized equations. I did not go through that derivation because, quite frankly, you guys are never going to need to know the derivation. I do not need to know the derivation. It's just I just take those equations as fact for transformations. All right. Now, the things that are important for Mohr circle are this. So this sigma x plus, actually, I'm going to continue just writing these equations really quickly. So sigma yt was basically just the same thing, but instead it was subtract. And then tau xyt was negative sigma x minus sigma y divided by 2 sine of 2 theta plus tau xy cosine of 2 theta. And of course, these were for when our shape was rectangular, like this, and our stresses were sigma x, sigma y, and then tau xy. Right, everyone remember that? Good. So, some things that I just want to point out. Firstly, this sigma x plus sigma y divided by 2, what does that look like? It just looks like the average of the x and y stress, right? It's just the average of the two. So we call this sigma average. Sigma x minus sigma y divided by 2. It's not really an average, but it's half the difference. In practice, we call this sort of like a deviatoric stress, which is a type of shear differential. The symbol I like to use to call this, some textbooks don't use a symbol, I do. I call this Greek letter lambda.
Lambda?
Lambda.
Oh, lambda.
Yeah, LAM BDA. And these are important coordinates, right? So the way that Mohr circle works requires these terms. So we can plot these stresses in sort of a plot. So one of the things I will do is just create this plot right here. Let me use a small eraser just to erase all of this. Where we can have stresses plotted on both the x and y axes. So the important thing that we really need first off when we're developing these circles is sigma x, sigma y, and tau xy. And we use those values to generate these coordinates within the plot, which will use sigma x, tau xy, and then sigma y, negative tau xy. Now, when you're plotting these circles, you'll obviously have numbers, but I'm just going to say for this coordinate 1 here and then this coordinate 2 here, I'm going to use blue for 2, actually. Coordinate 1 can be, I don't know, like here. And then coordinate 2 can be like here. From there, you can kind of draw a line directly connecting these 2 points. This black point here, anybody want to take a guess at what point that is?
The average?
Yeah. I should also note, the x-axis is going to be your normal stress, and then the y-axis is going to be your shear stress. And then that middle point is going to be sigma average. I'll call this coordinate 2, and then this is going to be coordinate 1. From there, you can just kind of draw out your diagrams to look really nicely if you really wanted to. And what we will get then is you can kind of formulate a circle. This average stress is going to be the center line of our circle. So let me just draw out a nice big circle. There we go. And that's our circle. That represents every single stress state possible. Anything, single value that falls on that line. This term here is that lambda value that I was talking about. It's just the lateral position of the stresses. Does that make sense so far? How this circle is first produced? Now, just a little bit of, I guess, context just to explain a little bit more. We can then break up this circle based off of rotation. So this line right here I'm actually going to use a purple line. The purple line is what we call the origin of planes. Basically, this is the line in which this stress state up here, the given one, occurs for that given Mohr circle. So it's the origin. It's basically how the problem starts. That's the reference plane for this problem. Now, if we were to rotate it, we could rotate it that way, we could rotate it that way, and then we would get different stress rotations. For example, if you wanted to rotate it 22.5 degrees, then we would be able to find an orientation for a stress block that's 12.5 degrees rotated. Now you might be wondering, why? It is because every single rotation is half a rotation, half an angle. Every angle in the Moore circle is half an angle in practice. This is where, in the equations, why we're using a 2 theta. Because then every single angle here we could just say is just 2 theta. Are there any questions so far?
So again, for the inside the circle is the maximum of how something can deform. You're saying where
Not the form, but it's the circle represents any single stress state possible for any given rotation. So, for example, if you wanted to find what the stresses would be if you rotated that that block, like, I don't know, let's say you wanted to rotate this thing 10 degrees, then the way you would do that is you would rotate this thing 2 times 10 degrees. So it would be 20 degrees. Does that make sense? And the best way to think about why we're doing that is because if you were to rotate this thing, this block 180 degrees, it would just be itself. Because this stress would just be pointing in that direction, and it's sigma x. This stress would just be pointing up as sigma y. And then tau xy would just be pointing up here, and it's just tau xy. So because of that, we only really need to consider rotating this block here 180 degrees in order to get every single possible stress state imaginable.
Okay, so because it has to be in equilibrium, we're just basically solving for one of each, but because it needs to be in a state of equilibrium, we multiply it by 2 because we're time for the other side. Because if you look, like what you said, if you rotate 180 degrees, everything would be the same.
Yeah.
It's basically, it's just double.
Yeah. So in Moore circle, instead of solving for half a circle, you basically just, if you were to rotate this thing 360 degrees, it would just be 2 circles stacked on top of each other. So it's like, why result in that confusion when you could just use 1 circle and just set the angle equal to 2 times whatever rotation angle you use. All right. So that means, let me just add a little note here. This is why the angle is 2 theta in the equations. Now, we had some key terms last class. What are some of the important points or the maximum values that we would use in the design? I'll give you guys a hint. What did I ask you guys to solve for the get out of jail? I know I didn't post a get out of jail. It's because I didn't print one, and so I put it on the board. So I'm going to leave this question for everyone else to solve. Principal stresses. And where did the principal stresses, what was the condition for the principal stresses? What were they?
Sigma 1 and sigma 3.
Right. And what did those represent?
The maximum end.
the maximum and minimum normal stresses within a problem. What is the shear stress for the principal stresses?
Tau max.
Nope. If you guys look back at what your principal stresses are, look at the stress block. Where do you see a shear stress?
Could you repeat the question?
What is so Michael said that the principal stresses are the maximum and minimum normal stresses. What would the shear stresses be associated with the principal stresses?
Is it just tau XYT?
Not quite. Because tau xyt is just a general equation we use to represent the shear stress along any principal axis. But it's a very specific value for the principal stresses that the max and minimum normal stresses are. You can see it on the Mohr circle if you look carefully enough.
Plus or minus 45?
What? No, that's the that's the rotation or the change for theta s and theta p, which I'll get into in a minute. But it's very important to know what the shear stress is for the principal stresses.
I mean, we solved it by doing the tau XYT just with the different angle.
Yeah, but there's an associated shear stress explicitly.
Average stress?
Not quite. Average stress would be like the normal stress. Let me look back. Let's look back at the notes then. So the principal stresses, sigma 1 and sigma 3, are 3.83 and negative 1.83 here. Let's look at this stress block. That's the stress block for the principal stresses. Do you guys see any shear stresses there? No. So because of that, wherever you have a principal stress, the shear stress is 0, which tells us, you were asking something?
Hold on. I said 0.
Oh, yeah. I didn't hear you. My bad. This means that our shear stresses, I'm just coloring these in just to make them more visible. Our principal stresses are here and here. And if you guys remember, sigma 1 is always going to be on the right-hand side of the circle, and sigma 3 is always on the left-hand side. So this is the maximum principal shear stress, sigma 1, and the principal shear stress, sigma 3. What about the maximum shear stress? What was the normal stress associated with that? What did we say the maximum shear stress was? What do you guys think it would be? Take a look at it. All right, shear stress is along the y-axis. What's the maximum shear stress on the circle? If the shear, what?
Coordinate 1.
Not quite, because you see there's still parts of the circle that are above it, which means there's stress planes that are higher than the current stress plane. Yeah. Top of the circle. Which I will use green for this one. Which this would be tau max, which will always coincide with the stress average. So, sigma 1 and sigma 3 occur when tau equals 0, and then tau max occurs at sigma average. All right, so those are all of our important points. But then the issue becomes, how do we solve for tau max and sigma 1 and sigma 3, all without having to use the equations? Because those equations, like, they can be useful, but they're a pain in the butt when trying to plug and chug stuff, right? Well, we need to understand the geometry behind these circles. So one of the things I personally like to do is, what other shapes do you see inside of this circle, just right off the bat? You see a triangle. I bet you're looking right at this one too, right? And obviously it's on the other side too. So what I am going to do is just draw this triangle real quick. Just right up here. And then I'm going to just use a small stroke eraser just to do that. All right. So we already determined that the horizontal length of this is lambda. What about the height? What would the height of this triangle be? Not quite. Well, I mean, it just any value, because it doesn't necessarily have to be 2. Like, these could be scaled up by like 5, 10, 15, 20. You know, it's tau xy. It's the original shear stress. Which means that we can determine what? We could determine the hypotenuse, right? What is the hypotenuse going to equal? What about the circle is the hypotenuse equal to?
The radius.
The radius. Exactly. So we could call that r. But what else do you find interesting about the radius? What else is the radius going to equal? Do you guys agree with me that the radius is also technically equal to tau max? Yeah? So we could just replace r with tau max. So the maximum shear stress is just the radius of the circle. How do we determine that? Tau max, which is equal to the radius. What do you guys think? What would tau max equal? It's a right triangle. Say it, Edgar.
Lambda squared.
Yeah, you're thinking Pythagorean theorem, right?
Yeah.
Yeah. So it's just the square root of lambda squared plus tau xy squared. And one of the things that I do just want to note really quickly is the angle here, because this right here would be the plane for principal stresses, right? Because there would be no stresses there, right? So like if we look at it from this plane onwards, there's no shear stresses occurring along that axis, right? So that would be the principal stress plane, which we would call this 2 theta p, which if we wanted to find the normal principal stresses, we can rotate our original plane 2 theta p in the direction, in the rotation in which we get to the principal's plane. So, using this triangle, we can also figure out what the principal stress plane it would be. This would be, we could say tangent of 2 theta p is equal to what? Just tau xy over lambda. Which then when you expand this further, you get theta p is equal to 1/2 tangent to the -1 tau xy over lambda. But what did lambda equal? Lambda equals sigma x minus sigma y divided by 2. So this just becomes 1/2 tan to the -1 of 2 tau xy over sigma x minus sigma y. Does that equation look familiar to anyone? If not, look back at your notes from last class. Anybody recall that equation? Cool. And so concurrently, we know that because this angle is a 90-degree angle and that this is 2 theta p, what do you guys think this is? It's that 2 theta s that we were talking about. Does that make sense to everyone? Because then we get that 2 theta s plus 2 theta p is equal to 90 degrees, which is where we get that equation from. Everyone see that now? Are there any questions at all before I continue? Yes.
Can you put the formula back?
Yes. Got it? Does everyone see where this equation comes from, though? The 2 theta s plus 2 theta p equals 90 degrees.
And what is that? What is S, 2 theta S?
The theta s is the rotation you need to take to get the maximum shear plane.
Okay, so theta P is to get it to
The principal stresses.
stress, and then theta S is to get it to the maximum.
Yeah.
Okay.
Mm-hmm. Yeah, so it's really just the angle of rotation you need to take from the original problem. So purple was the origin of planes, which would be this, which means if you wanted to figure out what the maximum rotation is, you rotate that block theta s, and then just plug in or rotate it 2 theta s on the circle. All right? So we determined that the maximum shear stress was tau max, which is just the radius of the circle. So what's left to figure out? Just sigma 1 and sigma 3, right? What do you guys think sigma 1 and sigma 3 are going to equal? Any takers? Just using the geometry of the circle. If we know the radius, what else do we know? We know the center point of the circle. Those are your 2 hints. Use the radius and the center point.
It's just going to be the diameter of the entire thing?
Not the diameter
You add the radius
to sigma average, right?
to.
Mm-hmm. And that gives you the principal stresses. So sigma 1 then is just going to equal sigma average plus the radius of the circle, which just happens to be tau max. And then sigma 3 is just equal to the average normal stress minus tau max. And those are all of the equations you need to know to develop Mohr circle. Now you don't need those really complicated equations that we drew up here. because now you can just figure it out using theta. But then the issue, or using the circle. But then the issue becomes if you want to try and figure it out on a certain rotation, then you really need to draw the circle to scale. Otherwise, it's going to be a pain in the butt to approximate. Does that make sense? All right. Now, the best way to show you guys how to do this is just with an example. And let's work with the example that we did last class, where that problem was this. So I will just copy that down to here. Yep, there we go. And then just delete that. All right. So we know from previously that sigma 1 was equal to what? We said sigma 1 was 3.83 KSF. Sigma 3 was negative 1.83 KSF. Tau max was 2.83 KSF. I gave you guys theta P, which was 22.5 degrees. And then theta S was 22.5 minus 67.5. Oh wait, this is the negative 22.5 degrees. Does that make sense to everyone so far? So, first step with Moore circle is just compute all of your general terms that you need to know. So I'm going to ask you guys really quickly, what are some of the key terms that we need to know for all of the equations? First one was the average normal stress. What was the average normal stress equal to?
Sigma x plus sigma y divided by 2.
All right, so when we throw that into the equation, what's our answer going to be?
3 plus 1 divided by 2.
Not quite.
I mean 3 plus negative 1 divided by 2.
Exactly. 3 plus negative 1 divided by 2, which gives us an average normal stress of 1 KSF. What else did we need to know? Lambda, which was what?
Sigma x minus sigma 1 divided by 2.
So that's going to be 3 minus negative 1 divided by 2, which is going to give us what? 2 KSF, right? From here, what can we figure out? Just use process of elimination. Figure out what we know, figure out what we don't know. So just as a quick reminder, let me actually box these. This was last class. Answers we know that sigma x was positive 3 KSF. Sigma y was negative 1 KSF. What was tau xy again? Positive or negative 2 KSF? Negative 2 KSF. All right. So we know sigma x, sigma y, tau xy, sigma average, lambda. What else can we figure out? Yeah. Tau max. We could determine the radius of the circle. And that's using the equation lambda squared plus tau xy squared, which we throw that in as 2 squared plus negative 2 squared, which, tell me what you guys get for that.
Zero.
Nope.
Oh, wait.
2.83.
2.83. Look familiar to anyone? It's tau max proven. Highlight that off. What else can we determine now?
The principal stress.
Yep. Sigma 1. What would sigma 1 be?
The average plus tau max.
Yep, so that's 1 KSF plus 2.83 KSF, which is 3.83 KSF. Look familiar to anyone? Cross that off there. What about the other principal stress? Sigma 3. What was that equal to? Yes. 1 KSF minus 2.83 KSF, which gives us negative 1.83 KSF. And that aligns with the sigma 3 we got last time. And just for the note's sake, I'm going to move this over and then just write out the equation also. Great. So now we've got tau max, sigma 1, sigma 3. The next step, plot it on your Moore circle. So let's develop this here. I'm going to throw this like that. And then I'm going to try and space these out as much as I can. 1, 2, 1, 2. As evenly as I can too. Please just mind my chicken scratch. 3, 4, 5. Denote on your axes, sigma and tau. The units are going to be in KSF. And so we know now sigma average was 1 KSF. So we'll say each one of these lines is just 1 KSF. So this is sigma average, the center of our circle. We had sigma 1 was 3.83. So that's 1, 2. This is probably going to be somewhere around here. Right. That's assuming a scale where each tick equals 1 KSF. And then we had sigma 3. I'm going to just I'm gonna extend that further, just a schmid. Extend that outwards a bit more. Yeah. And then sigma 3 was like here. And then we're just gonna have a circle. I'm gonna try and get my circle to look nice. I'm probably not gonna do too great of a job of it. God. Mine kind of more looks like Moore's sphere or Moore's oval. So let me like try and like fix this a schmid real quick. So that's 1, 2, 3. And then, yeah, that looks good, right? Yeah. This is kind of going to be slightly lower here. Our tau max value is just going to be this, which is going to be just up there, which should coordinate with roughly 2.83 KSF. It's not exactly hitting the 3, it's below it. And then some important things that we should also do is plot our original plane. So our original plane, I'm going to do this in purple. We had 3 and negative 2. So that would be 1, 2, 3. Wait, 3. Yeah, wait, 1, 2, 3. And then negative 1, negative 2, which should yield us a circle point roughly here. So this coordinate is going to align with sigma x comma tau xy. That's the 3 comma negative 2 coordinate. And then we're going to have another coordinate, negative 1, positive 2. That should really be closer to like here. And then I got to just rotate this, shift that slightly over, just to make it look nicer. And that's sigma y comma negative tau xy. And so we would call this line right here with some standard error in the diagram. Our origin of planes. Oops, wrong one. And that's our Moore circle. That basically describes every single rotation of stress that we can consider within the problem, all without having to use any equations whatsoever. Are there any questions about this at all? You just shook your head yes, but I don't know. No questions? Yeah. You can use it, but you can also just use the equations because the equations are derived directly from the angles. So my personal preference is generally like, if you want to determine what this angle would be, if you wanted to find the rotation you would need to find the principal stresses, you would just rotate this 2 theta p that way. And then from there, you would just find that tan of 2 theta p is just equal to tau xy over lambda. Because this value here, this highlighted distance, that's your lambda value. So we could do that real quick. Your tau xy would just be the -2, and then your lambda, we computed it as 2. So it's -1. So we take 2 theta p, which is equal to the inverse tangent of -1. Which should give you -45 degrees, which means that theta p is equal to -45 divided by 2, which is the -22.5 degrees. So previously, using the equations, I had given you guys theta p already. This is one of the ways now where you could just figure it out by just knowing a stress state. Otherwise, you really need to like do a lot of math, I guess, to figure out the principal stress plane and like know how to manipulate the equations in such a way that you can figure out theta p. And then if we wanted to find theta s, we can do 2 theta s plus 2 theta p is equal to 90 degrees. So 2 theta s plus 2 times -22.5 degrees is equal to 90 degrees. 2 theta s would just be 90 plus 45, which would be 135 degrees. So theta s is just going to equal 67.5. And that's how you would find the planes. Are there any questions about this at all?
Could you go back down just to that second formula?
This one?
That green one,
Yeah, this is just using that equation that I had given you guys yesterday with the relationship between theta s and theta p. It's just now we understand why that equation exists. But everyone understands why we're using 2 theta instead of just theta p plus theta s equals 90, right? Like it just has to do with the fact that if you were to just rotate the entire block 180 degrees, it just repeats itself. So we just multiply the angle times 2 just to then change 2 circles overlapping each other to 1. All right, I'm gonna give you guys about a few minutes of break and then we'll do another problem. me see something.
Deserving question. Yeah, I think deserving. Basically, it is the best ice cream there is. She's talking about cocoa and all of it. It's the ice cream business I don't think so. Yeah, let's put that in the name. No. You can just do chilies and we don't use it. Halal? No, I like halal. It sounds like you must be. Who put halal food? Oh, you never tried it? It's so good. It's so sweet. You go to? There's Naz's halal. Ours is the Oh, Shaw's, yeah. Shaw's. Shaw's, dude. Yeah. Shaw's or Shaw's? Why is it all the time? I think they're both pretty close. Can we add chilies again? I only eat chilies. Maybe it's a cookie zucchini. A cookie bazooki. Do they have this at Chili's? Applebee's. Chili's, right? Chuck noodle? She doesn't want to. She doesn't want to try it. That's why she keeps asking. I choose little times.
All right. Anyone remember this problem? From when we get out of jail? All right. Plot the Moore circle for this. All right. Why did everyone hate this problem last class? This one was so easy.
Because there was no info, and I told you what it was, you said yes, and then said no. You're playing mind games.
I know, I'm toxic.
That's what I thought. It was equal to 0, 0.
You shouldn't be, but it's a good tool for anyone. Yeah, you shouldn't have to use the information from last class. Who here's got it? You do, Christian? Or you were raising your hand for something?
It's just for a specific,
So
specific
does the
for
other
the
one.
original stress. So this is the original stress.
This far.
This over until the, yeah, that was considered to be where it was playing.
Yes.
What would you do in regular?
Yeah.
Okay. Say S is 0, but your P is 45. How would you? Oh, no. That's not.
What's the origin of planes? What would that look like?
Like random.
Yeah. So theta s would be 0, which means if you rotated that 45 degrees in practice, then you would have to rotate it 90 degrees on the circle, which would give you that
It would
theta.
just be the middle here. 45.
No, it would be 45 here, which then would be 2 times 45 here, so it would just be 90. So it makes sense.
Oh. Yeah. So we still draw the,
The origin of planes is just the vertical line straight through.
so we're gonna draw,
No.
P.
Theta p is just going to be a 90 degree angle. So you could just say, yeah, you could just take the origin and then just draw like a little arc. Basically, it's this entire thing there. Yeah. All right, I think everyone's got it. Who here doesn't have it? Mike, you got it? How about you, Edgar? You got it?
No.
All right. Well, let's go through it. You should have something that looks like this.
My circle doesn't look like that.
What?
My circle doesn't look like
That's
that.
exactly what I have on my paper.
But that is what I got though.
It is? Good.
What happened was this.
So, this is how the stress block would look for the original loading conditions. The only thing is it doesn't change the arrows, it just changes the negative symbol. I changed the arrow direction and just leave the number the same, so they're both the same thing. And then when you rotate it 45 degrees, where is it? This is how the principal stress plane should look. Make sense to everyone? The shear stresses, it shows the arrows, but the actual magnitude, if you look carefully, are just 0. And then the principal stresses are 8,000 for sigma 1, which would be sigma xt for us. And then sigma y is negative 8,000. So as long as you had a circle with the center as the origin, and then a radius of 8,000, your answer is correct. My next question now is, using the circle, using your circle, determine sigma xt, sigma y t. I don't know why I put a comma after sigma x t. And tau x y t when theta is equal to, I don't know. Emily, pick an angle.
33.
Oh, you picked a fun one.
Is that really bad?
Might be. 33 degrees. All right, that's your objective. Find out what the transformed stresses are using your circles. If I go around and I see equations, I'm going to be upset. Use the geometry of the circle to find out what sigma xt, sigma yt, and tau xyt are. And in the meantime, I'm gonna help Edgar out a little bit since he said he didn't get the circle. Let me see what you were doing.
So. I feel like I'm, okay, so. I was trying to make sense.
No stresses in X, that's 0, 0, negative. That's where you're messing up. There's no normal stress.
Okay, so this would also be zero.
Yes. Normal stress would mean that the force is pointing directly at the face, which in this case, there's no force pointing at the faces.
Oh, okay, okay, because I saw it here, like, there's usually, like.
This is a positive 3, so that's the positive 3 there. It's pointing away from the face, it's perpendicular to the face. This one here, sigma y, is perpendicular to the face. These arrows here running along the sides are parallel to the face, so they're shear stresses.
Okay, and this would be,
Yeah, that's why this is negative 2 days.
okay,
So that's where you were messing. Yep, which would make sigma 0 plus 0 divided by 2 is what? 0 minus 0 divided by 2? 0. So just rewrite those really quickly, just to be 0. Yeah. Not quite. Theta is 33 degrees. So what would 2 theta equal? 66 degrees. So you need to rotate your plane 66 degrees. Your plane of origin, I mean,
Yeah, yeah.
which that requires you understanding what your plane of origin is in the first place. Do you understand what I mean by plane of origin?
No.
It's your original stress state plane. So, what was the original stress condition that we had? It was just
Here and all that, I understand.
yeah, and you drew out the circle, which is good, right? But what is our original plane if we were to plot it out? Right, you have 2 coordinates. What was sigma x? So write out your coordinates really quickly.
So that, so this one's 3. This one's 1.
That is sigma 3 and sigma 1.
Yeah.
But what about our initial stress state coordinates? Remember, I said use sigma x tau x y, sigma y negative tau x y, and that'll give us our plane. Do you remember that? That was, where was it?
This is what I didn't work.
That gave us these coordinates here. You remember those?
Oh.
Yeah. Write those out. That gives you your original plane. Yes.
Yeah. Did you do it?
Nope, I don't want you to.
Yeah, no, this is-
Geometry. Yeah.
Like 9 it in,
What?
did you just like 9 it in?
Yeah.
Because it's double that. Degrees is 66 degrees.
Yeah, you gotta use
What?
66 degrees on the circle, so you gotta figure out the geometry.
So this is our original
Look at that first one, by the way.
origin. You just, it's kind of
First
just.
one was beautiful too.
Mm-hmm.
Okay, how do you?
Which, you know the angle. What else do you know?
These coordinates.
No,
That's what that is.
Yeah.
It's not just a random,
Oh,
you know.
So you can figure out what sigma x is how it's y.
Yeah, no, I do. Don't ask me to
And then you just do the opposite
You know what's
here,
crazy?
and you can figure out sigma y.
Wait, you could-
And that procedure applies to everything, it's just for this circle, it's
Nah, I
gonna be
just feel
really
like you're
easy.
looking in it.
Because sigma
Yeah.
and sigma y should be equal to each other in magnitude, but they're gonna be opposite in some. Yes,
Oh, no, this isn't it. This is it. That's my circle.
this is why I say draw it to scale, because then it makes it hard to really
I
visualize.
got it.
Have you been using your circle templates?
Nope.
You have.
It's in
My
my
first
bag,
one,
too.
What?
It's in my backpack too.
my first one looked good for freehand.
Your first one looks good for freehand.
But then after that, I lost it.
Mhm.
This was the second.
I wanna see circle templates to say your
Yeah.
homework. If I don't see it, I'm gonna be upset. Cause if you tried showing that to like your client in the future, like your circle, it's like, was just like,
This is my template.
they'd fire you. They'd be like, can't draw a simple diagram.
So I have a question actually.
Yes.
I can see the circle.
So
I draw circles every day, because, you know.
those were the two coordinates that you gave us.
Mhm.
But how would we go about finding them here now?
But it's,
The
so,
Well, it's sigma x tau x y. So what is sigma x tau x y for this
you have
one?
to rotate.
That would be your coordinate one.
Which is that line.
I mean, sigma
Yeah.
x was just 0 and then
66.
Right, so write down your
So
coordinate
that would
one.
So.
That would be that,
half
that's your
of
coordinate
those.
one. And then that's
It's
coordinate
3/4
two.
basically.
Draw the
Oh,
line,
and then
that's your
just be-
origin of
And then I just drew
planes.
2 dots.
And then it would just be like that, just.
Yes,
with the-
so then from this vertical line, from this origin of plane here, you rotate it 66 degrees positively. Because otherwise, if I said when theta equals negative 33 degrees, then you would have to rotate it the other way.
So would it be like a moment counterclockwise is?
Yeah, it's basically the same rule. So 66 degrees would be in this direction,
Mhm.
right? And I say 66 degrees because it's 33 degrees here, so you would need to rotate it 2 theta, which would be 66 degrees. And then from there, you can use trigonometry to figure out what your coordinates are.
Okay.
Make sense?
Mhm. Thank you.
Yes.
So,
No, I did this,
Yeah, so that's your origin of planes.
Yeah,
So
like
I
for the
would
water,
keep it
that's
in these
great.
parentheses formats, not necessarily like this,
okay.
right? And then you would call that coordinate one, coordinate
He said you
two.
can do it,
Though
I'll just see.
it's
but
usually
we can't
expressed, can I
measure
borrow your
anything
pencil?
for circles.
Nope, not usually with a
You
negative.
could do an imaginary triangle.
So just use a comma,
Oh.
and then that's gonna be negative. So that's gonna be the positive, and then that's the negative.
And why is this is always negative though? Why is it negative?
It's just a, well, it's plus or minus. So this would be technically the positive tau x y, and that's
I will,
negative.
and I can.
Which then, because our origin tau x y was negative, it's just like that.
Okay. How do I
And the
do
reason we do that is because the radius of the circle, it's just gonna be your maximum shear stress is just always gonna be the same magnitude, because the center is always going to fall on that x-axis.
And this one's always positive and this one's negative?
You could use either or,
Oh, I
I
can
mean,
just choose.
Actually.
yeah, you can generally choose, though I like to stick with sigma x tau x y, sigma y negative tau x y.
Okay, I'll
So-
stick to that then.
Yeah.
So now I'm gonna
Really?
plot these.
Yep, so 0 and then negative 8 tau.
Zero, so that's here.
Not quite, because this is a shear stress.
Where do I?
So that's x-axis, x1
So
down, so that's your point 1, so mark that.
this is a
Oh, I
shear.
can see, I can see
Yeah.
like Euclidean.
And is it always gonna be a shear?
Yes,
Okay.
y is always shear. And then this coordinate, where's that coordinate?
Let's plot.
Yep, so mark that on your map.
Actually,
What are you actually getting
That's
into
all
these?
here.
Yeah,
I
and
just
then you just
Like
connect
if
the
you
two
actually,
lines.
because what it's asking is what are these 2 points now?
Yeah.
Why?
That is your origin of planes. That is the plane in which that problem, see how the rectangle is all loaded like that, because of the negative 8,000 shear force?
Look,
That
That's
plane
zero.
is for this
Zero,
one.
zero, right?
yeah.
Now,
These two were the
when you
sides.
want to figure out the
This was-
stresses, some angle theta,
This was
rotate
tau.
this
This
plane
was-
2 theta in that direction.
Another point
So
tau.
what are
One
Yeah.
is negative,
This
one
is
is
why I'm
positive.
confused. What
But
are
those were
these?
also the coordinates from before.
Those are to develop the circle.
Oh, I didn't even use that.
You can't develop the circle without those equations.
But I did develop it. I did it here, and that's how I made the circle.
Let me see.
I did this to make the circle.
Try doing it with more complicated numbers. For this problem, it's very easy.
Oh, so it just so happened to work out?
Yeah, because you got tau max, and then you got sigma average is 0,
So you just knew, okay, coordinate is 0, 8,000 radius. Otherwise, it makes it more complicated. There, it's, you can do it several ways.
When do I use this? Do I use this first? Because I understand.
That just explains what the angle you would need to rotate it to be to get into the principal planes, right? So really, I'm not asking you to find the principal plane or the principal rotation. I'm just asking you now, what is sigma xt, sigma yt, and tau xyt when you rotate the block 33 degrees?
Yeah,
Which then, how much would you need to rotate that by?
and then you multiply that by 2, so that's like 66.
you would need to rotate it 66 degrees, and then you find the stresses based off of the coordinate. Did you figure it out?
No,
What?
I was lost and then I started talking.
All right.
They were distracting me, that's why.
Here. We'll go over it.
Yeah.
So, everyone hopefully got that your Moore circle should be something that looks just like this, where the center would obviously be that. Your sigma average was at 0. Sigma, tau, and the units were PSF. And then these coordinates here were 8,000 PSF for sigma 1, 8,000 PSF for tau max. Sigma average was equal to 0. And sigma 3 was equal to negative 8,000 PSF. All right. Now, the next step that you needed to take after you developed a circle is you can plot your coordinates. And what this is for getting what our original plane is on the circle that gives us this stress condition. So this is our base plane in which all further angles theta are associated with, if that makes sense. So this would be for sigma x tau xy, and then sigma y negative tau xy. And this would give us 0 and negative 8,000, and then 0 and positive 8,000. Those are our coordinates. Normal stress is always in the left-hand coordinate for the x direction, and tau x, the shear stress, is always in the y direction. Once we plot this, we find that coordinate 1 here is located right down here. This is coordinate 1. Up here was coordinate 2. So we do a connect the dots. And let me just bolden that. And this here is our origin of planes. From here, I asked you guys to find what the transformed stresses would be when we rotated the block 33 degrees. So if we rotate the block 33 degrees, how much do we need to rotate the plane by? 66 degrees. Which would give us something like, oh wow, that's an awful shape. Something probably closer to this. So 2 theta is equal to 66 degrees. And from there, we can plot coordinate points where we know that this is going to be our sigma xt, tau xyt, and then this is going to be sigma yt, tau xyt. Wrong. I'm wrong. Because that would be tau yt, negative tau xyt, positive, and then tau xt. And the reason for that is because here was sigma x tau xy, which then needs to be consistent with sigma xt tau xyt. Does that make sense? So you can't just arbitrarily call it randomly. And then up here was the sigma y comma negative tau xy, which is just going to coordinate with that. Does that make sense? So they have to be consistent, the symbols. Don't just call them arbitrarily, like I just did on accident. How do we determine these points? Well, we use geometry instead of those really long equations. If this angle is 66 degrees, then what do we know about that angle? 24 degrees. All right. What shape does it form? A triangle. So this coordinate here is going to give us sigma xt, which means that the horizontal length of that triangle, this coordinate here, this is our lambda term, which is just going to be sigma xt minus sigma average, which for this case is just going to be sigma xt. Make sense so far? What about the horizontal? What is the horizontal going to be? Well, the height of the triangle is just what?
Sigma max.
No, not the height. Remember, what stress goes in the... Wait, you were saying sigma max?
Yeah.
Tau max.
Tau max.
Yeah, because sigma is for normal stress. Are you trying to refer to a normal or shear stress?
Shear.
Shear. So the height of this triangle is negative tau xy. And the reason why it's negative tau xy is because the shear stress was technically negative. Tau xy was a negative value. So a negative times a negative is going to give us a positive value, which is why it looks like that. It's a little weird, but the math will work out. So we draw a triangle really quick. This is just going to be sigma xt because we determined if that lambda is just sigma xt. And then the height was negative tau xy. This angle here is 24 degrees. And then the radius was that 8,000 psf. How do we determine sigma xt and negative tau xy? What do you guys think? Anyone? How do you determine now the shear normal stress, the transform stresses? If nobody answers, I'm also going to have you guys use the equations to verify.
Did you use like the Pythagorean theorem or?
Not quite, because the Pythagorean theorem would be used to find the hypotenuse or any of the missing legs. But the issue is that the components are both unknown. So,
You use sine and cosine.
exactly. Break it up into its components. So sigma xt would just equal 8,000 cosine or sine.
Why are you looking at me?
Cosine. So Katoa, guys. Opposite over hypotenuse. For sigma xt, it's adjacent. So this is 8,000 cosine of 24 degrees, which will give us 7,308.4 PSF, give or take. For negative tau xy, it would be 8,000 sine of 24 degrees which will give us 3,253.9 PSF. Make sense so far? Good. Now, you would follow the same procedure for the opposite side of the triangle, for the opposite side, but the circle's symmetric. You know, the origin is at 0. So can anybody tell me what sigma yt would equal? Anyone?
It would just be negative 7,308.4.
Exactly. I also just realized this is technically for sigma yt, so I'm just going to quickly update my terms. Minus 0. So this is sigma y t. So that would be negative, positive, and then this is sigma xt, which would just be that. So yeah, it's important to keep track of the signs. Oops, and I just... Any questions about this? Does it make sense? I need a visible nod from everyone, because if it doesn't make sense, then there's an issue. Yeah.
Would you recommend writing that on a flashcard?
If you don't know trig, then yes.
Well, I mean like the circle. Large circle.
Maybe some of the equations, but not necessarily drawing out the entire circle, just because, like, it's going to take up a lot of room on your card, you know? And my recommendation is less is more on your flashcard, because I saw some of your flashcards on the last exam and they were messy, and I noticed that a lot of you guys were trying to reference equations and being like, I forgot this equation or I forgot to write it, but it was clear as day on your flashcard. It was just buried within probably like one of the middle equations or whatever, just buried underneath a ton of other equations or squeezed together. So my recommendation, don't write so much on your flashcards. I know there's a lot of equations for this exam, but just try and not go overkill with the flashcards this time. That's my recommendation. Just try and remember the procedure by doing practice problems. All right, and as a reminder, I did say that the homeworks leading up to the exam would be due earlier. So the homework for more circle and stress transformations are due Tuesday, and that's just to force you guys to practice these types of problems explicitly. All right? Okay. I'm going to give you guys a get out of jail, and then you guys can go. Let's make the get out of jail in here this time. and give you guys a stress block.
You're going 70%. Still over.
Mm, all right, here's your get out of jail. Draw your Morse circle, and then I want you guys to do the transformation that we just kind of did, but this time it's being applied to a much more complicated loading. And fortunately for you guys, we don't do 3D Morse circle. Otherwise, there would be 3 circles. One for sigma x, one for the x direction plane, one for the y face, and one for the z face. Let me stop recording.